Hello everyone, it's August the 5th. Alright, let's do this. Why these days always these small ones? Oh my god. We have to return all the unique binary search tree. Binary search tree. Binary search tree is the left is going to be smaller than the root and the right is larger than the root, right? Okay. Well, I guess it just, you pick a root. You pick anyone to be the root, and then we can do a recursion, right? Recursion. And once we pick a value out, we have to go through, the whole thing again. Like this, we pick 2 out, right? And then the left, we can do, we pick 1, okay, as the root. And then 1, we can choose the left. Well, nothing is smaller than 1, so we can now do left, so we have to do right. And when we do right, we can choose to do, 2, or the right we can choose to do 3. Right? And then when we add 2, then we only have 3 left, so we can only do this. When it's 3, we can only have 1 left, so we have to do this. Oh, this is not right, because... Oh, no, this is right. This is right. Yeah, so basically you pick a value, and then you say, I want to do everything large. Yeah, it's a recursion. It's a recursion, so it's the same. It's the same, but it has to be giving me a list, right? It's giving me a list of values so that I can move on to the next one. Yeah, give me a list of values. Give me a list of values, and okay, give me a list of values. Can do that. We can try that. That's not right. Yeah, I think give me a list of values is a better way to handle this. You can say def create, give me vals. It's going to be a list of int, and we'll return a list of optional tree node, right? Doesn't matter what it is, and we're gonna return create, giving me 1, not I, for I in range 1 to n plus 1. That's it. All right, so how do we do this? So you're giving me these values, right? It's sorted. It doesn't really matter if it's sorted. So we're gonna say for each one, right? For each one, we're gonna create a root on this. Right? Each one will create a root, and then because it's sorted, right? It's sorted. We can say for I in range 11 vowels. Okay. Rest equal to this, and then we say root equal to tree node, val equal to vowels I. Okay, and then root dot left, left. Oh. It shall also be able to, hold a second. think I can, you know what? I think I can, what are you trying to do? I want to do func tools. I think I can cache this. Cache this. Now the state, oh, n is equal to 8. So if I haven't used it, if I've used it, I've said, no, I haven't used it, it's gonna be 1. I have used it, it'll be 0. So who has not been used? Okay. Yeah, so we pick something that has not been used, right? And then we will use it and we'll pick whichever's on the left-hand side. Oh, is this going to be making it a little bit more difficult, more complicated? Oh, no, not really. Not really. Yeah, like we pick something is gonna be root, right? And then we set all the ones on the right to be empty, and then we pass it to it. Or yeah, we set everything to the right, it will be empty. How do you do that? We can do that by, yes, we can do that. Or we can do that. And then every time we just go through. Let's try. This is actually an interesting problem. A state is going to be an integer. Okay, and for each time, we just say for v in range 1 to n plus 1. Right, and when we start, is everybody is possible, so it should be n. So it should be 1, left shift n, minus 1. Right? That's where we start. And then we try every single one. Wait, hold on. Every single value. I think this has to be n. Because 1 left shift once, 0 times, 1 time, 2 time. Right, it doesn't matter. And then we can say, because it's 0, 1, 2, 3, all the way to the end. So for each value, val shall equal to v plus 1. Right, we say this is going to be the root, and then the left all lefts shall equal to create something. Right, what is this something? Well, once I do this, we say new state, right, shall equal to state we shall set it to 0. How do we set one of them to 0? for v in range. Let's say for I in range. Okay. If one left shift I and state, then root equals this. Okay. If I do this new state, oh, exclusive OR. So state exclusive OR one left shift I. Because one left shift I, that position is a 1. And with the one left shift is a 1, 0, 0, 0. And now with exclusive OR with the state. So if both are 1, then they become 0. And all the others do not change. 0, 0 still 0, 0, 1 still 1. So we get a new state, right? We get a new state. And when we have the new state, the lefts, so the left subtrees, let's just say left subtrees is equal to create. So we're going to pass all the possible to the left. So all the possible on the left hand side will be this. So this is our state. You know, the state. And I say we are currently looking at this. So these are the ones smaller, right? So we should do one left shift I. So 1, 2, 3, one left shift I. So 1, 0, 0, minus 1. And then we end, so we keep these. So shall be new state, right? And one left shift I minus 1. Right subtrees. So you go to create. Now that's gonna be these things. How do I get this? So I need to have like 1, 1, 0, 0, 0, 0. How'd you get 1, 1, 0, 0, 0, 0? Exactly. How'd you get this? Well, I can get this. I can get this, right? And an exclusive or this. No, I don't have to. I just need to get this. All right, 1, 1, 1. Because this doesn't matter. I already set it to 0. So I just need to set these to 0 so we get all the bigger ones. So I just need to say 1, 1, 1, 0, 0, 0. Set the remaining to 0. Oh, then I just need to do this. 1, 0, 0. So it's just one left shift I and one left shift I. So that should be new state and one left shift I. So now I have the left subtree and the right subtree, right? Then we can say for each left subtree, we can do it, right? And for each right subtree, I can do it. So for the new one, it could be there's nothing. All right, what if we have nothing? We have nothing, we just return nothing. Yeah, so I think we can say for left in, for right in, rest.append left equals left, right equals right. Right? But what if the left is a none? That gets nothing. So we're saying for each this if there's nothing, right? If I have to go through all this, yeah, if I have something, that would definitely will create something. If there's nothing, then we do have to. So I saying was in here, we say if not res, then res.append none. We have to append something. Then we return res. Okay, so return res if res, else return a none. What do you think? I'm actually not sure. We'll see. We'll see how it goes. Yeah, let's just do a simple one, see how it goes. Output 1. That is bad. 2 1 3 1. What the hell is this? Okay, that's not right. 3. All right, 3, 1 left shifts 3, 1 2 3. That's your 1 0 0 0 minus 1 1 1 1. So 1 1 1 pass in, right? So 0 1 2 3. So this is 0. I is 0, and it's true. So now I set it to this, and then we'll go new state. All right. New state will be this. This is 1 1 0, and 1 left shift is 0. So that's 1. 1 minus 1 is 0. And 0. So this will be 0. So create will be 0, which means on the left hand side, because I pick 1, on the left hand side is 0, right? So now this one is 0. So 0 comes in. None of them is right. So this one will return none. So the left will be none. The right in I is 0. So it's 1. So it's a 1 1, right? So 1 1 will be 2 3, right? We have 2 3. So 2 3 comes in. So this should append the current one. Left equals left, right equals to right. Don't understand. 2 3. 2 3 comes in. So it is 0. 0 cannot go. Now we can do 2. Right? We do 2. 2. I do this. So 2 can only do 3 on this side. It shall be right. Right? And then I think the problem is when we only have two. What if we only have 3 left? So this has to be 2, so it will be 3 dot append. Yeah, so it just says 3, right? I don't know. Why is it not right? Hold on. I have to debug this. 1, 2. One is right, and 2 is not right. I got 2, 1. I don't got 1, no 2. Huh? Why is that? And I have to debug. One, yes. Because I used this left, right. And I only did it 3 times. 1, 1 is the first one, okay? And then I is 0, new state. New state, I think this is the new state is wrong. Okay, I want to keep everybody on the right. So I do this -1. Oh, this is not right. I see. Oh yeah, I have to. Oh, I think I got it wrong. I see. I thought this was in. No, you have to include these ones. So, how do you get this? Well, we can do 1, 1, 1, 1, 1, 1 exclusive orders. Okay. So, which means here's what we're gonna do. It's the right. That's wrong. So it's gonna be. Hold on. 1 left shift and -1. Okay, so this thing exclusive or something. That's 1 left shift I -1. Okay, so let's change that. Try it again. There we go. Now we're talking. Now we talking. Yep. That's it. Took a little bit effort. A little bit effort. 95. Since n is small, we can use dp and bit mask to record the state of which values have been taken and which have not. The difficulty. Oh, difficulty is to figure out the available states for the left and the right subtrees. The total number of trees. Well, given this, how many trees do you think there should be? That's a good question. If I have one value, that's 1. 2 values, that's 2, right? 3 values, I pick 1, then we have 2. 2 is going to be 2, right? So we have 2. We'll pick this, that will be just 1. That'll be 3. We'll pick this, that'll be 2. So that'll be 5. Right? 1, 2, 5. Right, 1, 2, 5. And now we have 1. And we can actually try this. Right? We say n is 1 is 1. And as 2 is 2. Right? And then 3 is 5. And as 4, we can do 1 plus 3. Yeah, we can do this. This, 2, 3, 4. To pick this is root. That will give you 5. This is root. This is only 1. This 2 will give you 2. So this will give you 2. This is root. This will give you 2. This will give you 5. So 4 shall equal to 14. All right, 5. So we can have 14 plus 1 times 3. 3 1 times 5 plus, yeah, but here's 4. Right, 1 times 5, 2 times 2, 5 times 1, and then just 4, 14. Hard to say. This is 28, 38, 30 plus 4, 42. I would say 2 to the n. I don't have a good idea why it's 2 to the n. Is there a reason for that? Hold on, let me just see what solution I used in previously. Recursive DP. For left and right. Catalan number. Gn is the nth Catalan number, is in 4 to the n divided by, oh my goodness, n to the 1.5. L and R. Left about -1. Oh, we pick a value for val in this range for each one. Oh my god, this is great. This is great. Yeah. That's a range. That's exactly what it should be. You pick a value, you have the range on the left, range on the right. Oh, it's better than the one I have. The one I have will have a lot of. Yep, that's the one. Yep. Okay, let's try this. A better solution. I mean, this is not bad. It's okay. But we don't have to do state, which is to do low and high. Right, say produce all BST in the range low to high. Say if low is larger than high, then we'll return none. Otherwise return. There we go. For V in low range, low to high. Right. Then we say for left in create low to V-1. For right in create V+1 to high. +1 to high. Right, that's the range. We pick this, and then we have the left and the right. And yeah. Then we'll do tree node. Val equals V, left equals left, right equals right. And then return, create 1 to n. There we go, that's the one. Oh, it's even faster. I think I did not cache them the previous. Oh, I did cache. Yeah, I don't know. Much cleaner solution. All right. So, looking at this, try one by one. So I have one more idea. So I want to try. Go back to the hint, right? The hint said do this, this, this. So this is what I'm gonna do. All right, this is what I'm gonna do. We are going to go through every edge. All right, we go through every edge. But there is a big difference. I think I tried this one before, but basically we go through every edge, okay? And we're using the ones, using the path ones. And then we find the minimum of this one did this two. And the ideal is because everybody is one. So whatever I find right now is the smallest, right? It has to be the smallest. And then if I turn all the other negative edges into, a giant value, then the minimum shall maintain. That's kind of the idea, right? So we say we go through every edge right? We go through every negative edge and use graph once to find the every negative edge AB to find the min path from S to A and B to D. Since we are using graph once, the paths we find must be the minimum path, even when we make modification to the weight of of AB and increase all the other negative edges to max value. So that's it. We should say for AB in edges. Okay. Then we say PSA path SA and WSA equal to self.extra n graph 1 source A. So the same thing. BD, okay, BD, there's gonna be B, there's gonna be destination, okay. Then we're going to say, we're going to try to find, we say if WSA, right, plus WBD is smaller, just follow this, smaller than target, right, then we can set we can set the weight what we have to be AB. So yeah, we know AB is going to be target minus this and minus this, right? So we're going to go through this path. All the negative edges inside has to be, you know, the maximum. Oof. Yeah, and this one, we're done, right? We're done. So we say neg edges ones hold on, how can we do it easier? So the result is going to be, we go through this and we set it to 1. Okay, so we go through this to set everybody to, oh, is there any easier way to handle this? I guess there is a easier way. So we can say edge weights, do a dictionary for UVW in edges. Oh, that's neg edges, right? Neg edges. So for this in edges, UV equal to W if W is larger than 0, else max value. Okay, then we'll go through this. Of course, edge weights No, no, I don't like this. I don't like this. We can use the graph max. We use graph max. Yes, we use graph max. All we need to do now is say graph max a b equal to target minus WSA minus WBD. And we'll do the same for BA. Okay. And for I in range plan path SA minus 1 UV equal to path SAI path SAI plus 1, right? And then we say if UV in negative edges or VU in negative edges, graph max UV equal to 1 equal to graph max VU equal to 1. Ah, I didn't realize this. Oh man, can save so many lines. Can save so many lines, man. Didn't realize. Okay, so we set this to 1 if this is in, and we do exact same thing. We can use J, but let's just keep using the path BD, right? Path BD, this is path BD. We set this to 1. Once we're done, I think we can just return. Right? Yeah, we don't even need this. I think we can just return. And of course, there's nothing, then we return this. We cannot find any. Graph is not defined. Of course, graph is not defined. Okay, what do you think? I think we shall give this a shot. First, see if this one's correct. Took so long. What? How? I don't understand. I just did Dijkstra for source to A. What the hell? Oh my god. Wait, hold a second. Which part? Alright, something is not right. Something is not right. Must be something here. Oh, I guess you cannot do it this way. Why? Because that's the only difference that we had. No. What did I do? That was the same as before. I didn't do anything. The hell? Seriously, I didn't do anything. Yeah. I'm pretty sure that's exactly the same stuff. Oh, typo. Max. Oh, you gotta be kidding me. Ugh. Is not right? Zero, 3, 3. But I did change. Right? I did this at AB. I changed the target to minus. Five. Hold on. Why? Minus. Why would I expected 3? 5 minus 1 minus 1. I basically didn't change it. For path SA. For path BD. That is bonkers, man. What the hell? Let's print AB. Well, we know why, so I think we can put this back. Yeah, it's because of this. Shall be max. Okay, let's see. Something is not right. Print A, B, and then graph max A, B. 201. 20. I changed this to 1. So you have to try it. Oh my god. Yep, it cannot. You have to try it to see if it works. So if it's smaller, which is true, then you do this. Oh god. Then you have to say if check, right? So we say check path, check weight equal to self.extra and graph max source destination. Yeah, we'll have to check if it works. If check weight is equal to target, then you do this. Otherwise, backtrack. Backtrack. Oh, it's actually not that bad for backtrack. We just need to do for AB in, no, for UV in negative edges. Graph max. Yeah, all I need to change is these two, but you know what? I think so shall be the current neg edges. Let's say go to this. For this, if this. Screw this. I'm just gonna do this one more time. So everybody gonna set to max val. Everybody set to max val. Everybody set to max val. Then we just try it again. Yep. All right. Hopefully this is the last one. Hopefully this is the last one we have to do, and then we can claim finally this one will pass. All right, we're gonna try this. Come on, pass. Oh my god, I'm giving up. I tried everything. I seriously tried everything. Nothing's working. He's the last one. The last one says nothing is working. What the hell? It makes sense, right? It makes perfect sense. You find a negative path, and then you do a minimum. Alright, I give up. Spent way too much time on this. Hold on. Alright, finding the shortest path from the source to destination node in the graph. Adjacency, I do that. We use extra to find the shortest distance from the source. If the distance from the source to is less than the target, if it is, we know that is impossible. If the distance node is exactly equal, we modify all of the edges. Yes. If the distance of the node is greater than, okay, let's look, it's greater than the target distance, we iterate through all the edges in the graph. For each edge with a negative, we temporarily modify it to 1 and update the adjacency list accordingly. We then reply to find the new distance. If the distance to the destination node becomes less than or equal to the, we adjust the weight of the modified edge by adding the difference. Wait, hold a second. What? It looks so easy. If the distance to the destination is greater than, we iterate through all the edges. When this is a -1, we temporarily modify its weight to 1. We get it down, right? We then reapply to find the new distance. If the distance, so if we bring it down, then we find a new distance, the destination becomes less than or equal to the target distance. We adjust the weight of the modified edge by adding the difference between the target distance and the new distance. We change the weight of the remaining to a large I was doing this. We modify the weight to 1, okay? And if the distance to the destination node, right, as the distance becomes less than, we adjust the weight of the modified edge by adding the difference between the target distance and the new distance. So you're saying if I bring something down to 1 and that causes, so we go through every single negative edge. Okay, we turn negative edge to maximum first. Okay, then we'll have that, and then for each edge, right, for each edge, we'll modify it to 1 and to see if the minimum has changed. Okay, so we say now the minimum changes, then we will, but if it's not, then we have to keep going. So we modify the -1, so everybody will be super huge. Okay, so now we modify it to -1, to 1, and it's still big. Okay, then we go to the next one, we modify to 1 and it's still big. And after some edges gets modified, now the negative drops down, right? Not a negative. So which means after we modify the current one, the minimum goes down. So I just need to turn the current one back up, and then that shall do, because this is the current. So we go from some value is larger, right? And then we do this and then drop below, right? Which means if I go to back up, so if we don't do this, and it will still be above the target, it's because the current edge gets dropped below. So now we get below, so we can just keep adding it back up. So I think what this one means is we will do the max. This is good. We don't do the ones. Okay, we don't do the ones. We go through it directly. So this say we go through each negative edge AB and reduce its weight to 1. If by doing so, the minimum distance, minimum weight from source to destination drops below the target, right? That means AB plays an important role, plays the key role in reducing the weight. Thus, we just need to bring AB back up such that the mean weight reaches the target. I think that's it. So in this case, I don't even need ones. All I need is a max file. Right, now we can just say for AB in negative edges, we just turn it to 1, so it'll be the smallest, right? And we'll just say current weight self.extra and graph max source destination. If current W is smaller or equal to target, that means it's because we change AB to 1 to bring it smaller to target. So now what we need to do is to make this one bigger, right? So B shall plus equal to target minus current, right? Then we can return this thing because it's already the smallest, right? By doing this, we're already finding the smallest. Yeah, it's because this dropped down to 1, right? The current edge drop, that make the minimum goes down, right? If it doesn't change anything, the minimum won't go down. Otherwise, we'll return this. Okay, so let's try this one. We'll upload this. Oh no. I have to recopy and paste the test cases. Shoot. But that's okay. I have all the test cases. Alright, is this one? Does this one work? Oh my god, I think this one works. Well, not able to do it. Even after reading the hints. In fact, I think the hints are a bit misleading. Right? I think the hints is about a little bit misleading. Anyway, this solution explains it the best. Right, we basically set all negative edges to max val, right? And check some after checking some edge cases. We go through the neg edge one by one. For each one, we set it to 1 and see if the mean path weight drops below target. If it does, that means the current edge is critical. And we can increase it a little bit to reach target. And that target and then that path will remain the min path. Okay. 4 days. 3 or 4 days on this. Do it one more time. Make sure everything's correct. Oh, I don't even need this. So I can delete that. There we go. No, we're still not right. Oof. Finally. I mean, it's not really that. I don't know. I just got stuck. on this one. 4 days. I just got seriously stuck on this one. I mean, it could work, the official one. I mean, I can get everybody to 1 and then try it. It's kind of like we don't have to go through every single one if it's not possible. Yeah, you know what? Maybe we should. Hold a second. Let's pull out one of the previous solutions. Yeah, you know what? All right, let's just write it. That's fine. It's not that hard to write. We get ones. Right. Basically, these will be ones. This will be ones. And it's not too big a deal. This will be 1, right? And then we'll do this. Special case, and we'll do this. Hopefully, I can get a little bit faster. Update. Still do the other edge case check with all neg edges turning into ones. Hopefully this can speed up some test cases. Alright, let's try this. Will this be a little bit faster? Not really. So I'll stick with this. Oh, that's it. Gosh. Alright. That's it. So many days spent on one problem. I'll see you guys tomorrow. Adios.